Begin. So two things about cosets. One thing to keep in mind is raisin bread. Okay. Your group.
Say that on your video.
Your group is a loaf of raisin bread. And cosets slice up the loaf so that they're the same number of raisins in each slice.
Okay.
One of the slices has your group identity. There's one special slice that is a subgroup. All the other slices are not subgroups. If you actually you can compare this with linear algebra, if that doesn't bring up bad memories. Now, if you got if you got a three-dimensional space, right? You can divide that into planes. There's only one plane through the origin. Jesse, you're still on.
On Google Hangouts.
You're still on Google Hangouts. Or maybe not. Well, it sounds like somebody's there.
Is somebody else there?
Maybe somebody else is there. Anyway, all right. So not to get distracted. Okay. So you've got your three-dimensional space, and you have planes. Only one plane contains the origin. That plane that contains the origin is a subspace. None of the other planes are,
Yes.
because the subspace has to contain the origin. And this is in fact, that's a special case of coset, of the special case of this. All those parallel planes you can consider as cosets. They are translates of the one subspace. They're copies,
And these,
but they're not subspaces themselves.
and they are mutually exclusive.
They're mutually
sets.
exclusive, yes. It's a partition.
Okay.
It's a partition. It divides the space up completely into disjoint sets.
Okay, because when I first started the chapter, it actually compared it to onions.
Yeah. Okay, well that's just because of the Shrek quotation.
And, yeah,
I think raisin
with the
bread is better.
layers.
Yes. Well, in this case, each layer is the same. So it's a very big onion with parallel layers. All right, so the other example of coset is modular arithmetic. Now, you have the numbers mod n. Like, let's take the numbers mod 5. 0, 1, 2, 3, 4. All right, so that's 4 of them. Now, or here, let's do mod 3. It's right because it's right here. All right, so you can think of 0, let's do mod 3, you have 0, 1, and 2. 0, 1, and 2. Now, you can think of 0 as representing all multiples of 3. Right? Because when you add two numbers that are 0 mod 3, they're still 0 mod 3. They're all 0 mod 3. All these numbers are 0 mod 3. But you just choose 0 as a single representative of all of these numbers. Then you have the 1 mod 3. All these numbers, 1, 4, 7, etc., they're equivalent to 1 mod 3. Right? And a 2 mod 3. So instead of thinking of three numbers, 0, 1, and 2, you can think of three classes of numbers. Three classes of numbers. So you're dividing the integers into three classes of numbers. So it's similar. Now these don't look like layers, but they are dividing all the integers into three groups. So let me ask you, which one of these three corresponds to a subgroup?
I would think 0 mod 3.
Yes. Yes. It is a subgroup. Because if you take any two things in here and add them, it stays there. Whatever starts there stays there. And the zeros there, the inverses are there. In fact, this is the group you'd call 3z, and that's what it says down here. So you can actually represent these three sets as 3z, 1 plus 3z, and 2 plus 3z. So this notation means you take 1 plus every element in this set here. So that's your deal. All right, so here's some exercises about that. Now, this looks a little different, but it's really the same thing. And the reason why it's the same thing is that the operation up there is plus. So what you really had was something like 1 plus a subgroup, 2 plus a subgroup. Now, in general, the operation is not plus. We write it just as times or just as next to it. So this GH corresponds to 1 plus 3z, where the G corresponds to the 1, and the big H corresponds to the subgroup. So if you have a multiplicative group, instead of taking one element and adding it to every entry in the subgroup, you would take one element and multiply it by every entry in the subgroup. And we'll see examples of that. Like in matrices. It turns out, I just kind of give an example, I don't know if you saw it, but if you take matrices with determinant 1, matrices with determinant 1 is a multiplicative subgroup of the matrices with non-zero determinant. I think we've talked about that before.
So little g, or lowercase g,
Yes.
would actually be considered the remainders for the mod.
Yes. Well, but more than that, because in fact, I could take 1 plus 3z. I could also take 4 plus 3z, and it's the same coset. I don't have to take
all right.
I don't have to take something between 0 and 3 anymore.
Okay. It would just be easier doing
Yeah.
it that way.
So the thing is that now what we're doing here is, instead of we're turning subsets into elements. Before we were thinking about single element 0, 1, 2. Now we're saying that whole subset is an element. And looking at those subsets, and we're defining operation on subsets. All right. So here's another example of permutations. Let's look at this one.
Yeah, I read this and I got confused.
All right, so let's go through this then. Let H be a subgroup of S3. Now, S3 is all permutations of 3 things. How many are there?
6.
Yes, 6. All right. Now, what else? We have a geometrical model of S3. Remember what it is? Triangle. Symmetries of a triangle. So, however you can flip a triangle around, that's S3. Any element of S3 corresponds to some flip of a triangle. You can flip it this way, you can rotate it, you can do some combination of flip and rotation. They're all together, there are 6 of them, and they correspond to the 6 permutations. All right, so for instance, what does this correspond to geometrically? 1, 2, 3.
rotation.
That's a rotation. And here's another rotation. So in fact, I don't know if, I think we talked about this, that this is the rotation subgroup. If you just rotate the triangle, that's a subgroup. If you don't do any flips, you just stay in the plane, then it's a subgroup. It's a flat land. So that's going to be our subgroup big H. Now notice the subgroup has 3 elements, and the entire group has 6 elements. So in fact, it fits in exactly twice. And that's not an accident. That you show later that these subgroups always fit in a whole number of times. And that's the whole raisin bread idea. You don't get half a slice at the end. You always get whole slices. Right. So here, if you take this subgroup, so these are not all of the elements of the rotation group. Can you tell me some other elements of the triangle rotation group? I mean, triangle symmetry group. What else can you do to a triangle besides rotate it?
Yeah, you can flip it.
All right. So what permutation would correspond to a flip?
That would be the 1, 2, 1, 3.
Yeah, 1, 2. 1, 2 means you keep 3 by itself, and the 1, 2 switches around. All right. So I can multiply these 3 rotations by any one of those flips. All right. So let's see what happens when I do that. All right. Well, so what it says here is, if I multiply every rotation in this set by another rotation, then I'll always get the same set of rotations. Right? For instance, if I take 1, 2, 3 times H, then this notation means I take 1, 2, 3 times every element of H. So I get 1, 2, 3 here, and then I get 1, 2, 3 times 1, 2, 3. You can work out that that's 1, 3, 2. And then you get 1, 2, 3 times 1, 3, 2. You can work out that that's 1. So if I take this element times this set, I'm going to get this set again. And same with this one. So are you tracking with me? Does that make sense?
Mhm.
So here we're using multiplication instead of addition. Now, but something different happens if I take these three and I multiply it by 1, 2. Yeah, 1, 2 times this is 1, 2. So we'll do a little practice. What happens if I multiply 1, 2 by 1, 2, 3? Maybe I should pull up my OneNote.
Go to 3.
I should pull up my OneNote. Where am I? I'll just put it here and then fix it later. I don't even know what notebook this is. That's okay.
Cat research summary team.
Oh, okay. Well, then whatever. Okay. Okay. All right. All right. Oh, you have to add a section. I can always move this. So, oh, this has nice lines on it too. Okay. All right. So I want,
There are light blue lines.
yeah, 1, 2 times 1, 2, 3. So here's a good review. All right. So how do you start this?
Well, 1 goes to 2, and then 2 goes to 1.
Okay. So
1
what?
goes to 1.
So 1 goes to 1. So I don't even write 1. Then what about 2?
So,
2 goes to 3.
and 3
And-
goes to 3.
3 goes to 1.
1.
3 goes to 1, and then 1 goes to 2.
Okay, because I get 2, 3. All right, so we've got, so we want to take the coset, take the coset, 1, 2 times h, where h is equal to this set. Identity, 1, 2, 3, 1, 3, 2. All right, so we're taking that. Okay, so if I take, so I know that 1, 2 times identity times ID is equal to 1, 2. But then I've got 1, 2 times 1, 2, 3. I did that, and 1, 2 times 1, 3, 2. What's that?
Well, 1 goes to 3, 3 goes to 2. 2 goes to 1, so 3 goes to 1.
Yes.
2 goes to 1, 1 goes to 2.
Yes,
So 2 is
okay.
right, so.
All right, so you see what the result is. What the result we got is 1, 2 times h. I should do it this way. 1, 2 times h is equal to this set. It's equal to 1, 2, 2, 3, and 1, 3. Okay. And you can verify that if you take 1, 3 times h, or if you take 2, 3 times h, you get the same thing. Okay. So there's actually two distinct sets. So notice that the whole group S3 is equal to h, and then union. I'll just put a union here. This other set, which is I can write as 1, 2 times h. Right, 1, 2 times h is the same as 2, 3 times h is equal to 1, 2. So these are your two cosets. This is a group, this one isn't. So you divided your entire group into two parts. Now in this case it's 2 parts. In general you may have many parts. But the idea is the same.
Okay. So then I'm assuming with the right side, you would just flip it.
Yeah, you could do the same thing on the right side. In this case, I think you'd get the same cosets, but you don't always. You don't always.
Yeah, like H you do, but K you do not.
Yes, okay, K. All right, yeah, K you don't. All right, so good. All right, so, but you get the mechanics now.
Right.
So.
I love the permutations chapter.
Yeah. Well, it's, I mean, that's good because that's really the foundation of finite groups. Let me go on to section 2. Because my screen is... Where's the arrow? Oh, it's down there. All right, now, so we've already seen what I I've already mentioned what we're talking about is that cosets divide up the group into smaller sets. It's your slices of raisin bread. So what does that mean? That means that the sets have to be disjoint and they have to give you the entire set. So I apologize for this messiness here. I mentioned that if you go to the PDF, then you can see what this actually is.
Oh, I got
Yeah.
you.
It says proposition
Yeah.
14,
Yes.
2, 1.
Yes. No, unfortunately, the exercise numbering is not the same in the PDF.
No,
So use the numbering off of this.
I did.
Yeah. All right. So as I said, you divide your group into cosets. Now, suppose you have two group elements, G1 and G2. How do you know those are in the same coset?
'Cause it says
All right. So so there are different ways you can tell. There are different ways you can tell, and all of these are the same. So if you want to know two elements are in the same coset, you can use any one of these criteria. And I think you have to show that they're equivalent. So, for instance, this is saying that they create the same coset. If they're in the same coset, then they create the same coset. So we saw that, right? 1, 2, and 1, 3, they're in the same coset. And when you try to create the coset with either 1, 2, or 1, 2, you get the same one. Then, in this case, if you take the inverse of 1 times the second, that's in H.
And
You
that's
can-
why the 3Z worked, because they had the inverses.
Well, yes, they did. Well, all right. So if you look at 3Z, for instance. So for 3Z, we had 3Z, and then we had 3Z plus 1, and then we had 3Z plus 2. Now, according to this, it says, let's take G1. I hate why it does that. I don't want that capital. And it's going to give me a capital again. See it? Stupid thing. Okay, let's let G1 equal. So let's take 2 in here. So give me an element in 3Z plus 2.
-4.
-4. Okay. And then we'll set G2, and it's going to do the same stupid thing. Is equal to. All right, so far so good.
Because it wasn't at the beginning
Okay.
of the.
All right. So what's G2? What G2 is another one in 3Z plus 2. Give me another one.
-1.
All right, -1. That's fine. Well, give me something more interesting. How about
101.
101? Okay, very good. Okay, now, I don't know why it's doing that. I think because I did something wrong. I don't. Well, it's getting back at me for doing something.
That's exactly what happens to me when I'm trying to use technology.
Well, you gotta love it. Okay, equals 101. All right, very good. I fooled it. All right. Now, according to this theorem, G1 inverse G2 should be in 3Z. All right. So let's do that. So in this case, G1 inverse. All right. I just forget it. All right, you win. G1 inverse. No, G1 inverse in this case is because it's additive, right? So what's G1 inverse? It's the additive group.
Oh, the additive
Yes,
is 4.
it's 4. Additive group inverse is 4. So if I take, and instead of G1 inverse G2,
Well, G2 inverse would
We
be...
don't need
no, I don't need G.
Oh.
I don't need it.
No
So what I want here is not G1 inverse G2, but what I want is, in this case, what I really want is 4. It's going to be 4. Now, instead of multiplication, my operation is plus.
So 4 plus 105, or 101.
Yeah. So that's equal to. Oh, it gave it to me already. There's technology for you. Okay. All right. So
Oh, that's-
is that in 3Z?
Mhm.
Yeah, the division rule, right? You add up the digits to 6,
Yeah.
so which is in 3Z. Okay. So this agrees with this part 2. Okay. of, I guess it's proposition 14.2.1. Okay, so that's one
It is in
example.
the book.
No. Okay. All right. So then you can see the other ones. That if the two are in the same coset, then G2 is in the coset created by G1, and of course that's going to be true vice versa. Now that's actually not that. I'll give you this one as a throwaway. This is actually quite easy because if let's see here, how am I going to say this? Well, no, you have to do something. I was thinking the wrong way. But let's see. Can we see the relationship between this one and this one?
Are you saying 4 and 1?
Yeah, for 3 and 1.
3 and 1.
Well, one is if you multiply 2.
All right, let's see if we can do this. Let me do this. Just for practice. I think I gave you a bunch of these proofs to do.
Yeah, it's actually
Most of them.
A through D on the
Okay,
next
right,
exercise.
All right, we can do one. Okay, good. So let's do A implies B. And there's a bunch of hints at the end of the chapter. So let's do 1 implies 2. Well, it's like getting married. You have to adjust.
That's good.
All right. So we have 1, and we want to show that implies 2. So let's write down what we want to prove. So I want to start doing this because I think people get lost in the middle. So we're going to say, given. So what do you want to prove? So here's to prove. Given G1, G2, such that G1H equals G2H. Show that. Well, just write it down. In this case, it's pretty direct what you want to do. G2 is in H.
Oh, this is easy.
All right. So how would you? So it's proof. All right.
Well, if you're going to show an element, you need to,
So let's start out with a given.
Well, how
Yeah.
are you going to use the first property and go to the second property?
Right, that's the thing. So this is given.
so you could multiply both sides by G1 inverse.
All right. Let's multiply both sides by G1 inverse.
On the
So
left.
yes, that's very important. On the left.
Mhm.
Okay. Whoops, sorry. I should have copied it. Okay. And then here I'll just say left multiplication. Okay. Okay. All right, so what next?
So you got your identity with the G.
Okay, yes, okay. So I'll just put H, because that's the identity
Okay.
property. We'll just do that. Okay. So here I get H equals this.
Mhm.
Okay. This is identity property. Let's see. All right, so okay. All right, so this is a key step here. Remember what we want to show. We want to show that G1 inverse G2 is in H.
Well, we showed it up there, but only with numbers. We have to think abstractly now.
Yes, you have to show why it's true in general. So how do I go from here to the fact that G1 inverse G2 is in H?
Well, You know that G1 and G2 are in H, right?
No, you do not.
Okay.
No, you do not know they're in H. You only know this. In fact, in general, they're not in H.
Oh, right. Okay.
So think about what this actually means. This is a statement of equality between two sets.
Mm-hmm.
This set is the entire subgroup H. This set is G1 inverse G2.
Well, that would have to
Well, what
equal
if you
1.
say, suppose X is an element of G1 inverse G2? Then
Well,
that-
no, G1 inverse G2 is an element. You can't say X is an element of G1
yeah.
inverse G2.
Can we say that that equals 1?
What equals 1?
G1 inverse times G2?
Cannot, because they're not inverses of each other. There's G1 inverse of G2, not G1 inverse of G1.
Okay. I'm not sure this is going somewhere, but yes, no, that's going in a circle. Never mind.
'Cause
I was going to say substitute G2H, but that would take it.
No, you can't. All right, so what this means is that no matter what element of H I put in here, no matter what element I put in here that belongs to H, I'll get an element out here that belongs to H.
Right. But we're trying to show that.
No, that's what this means. This means that what we're trying to show is that G1 inverse G2 is in H. That's what we're
So
trying
how
to
do you
show.
say that? How do you?
So what I want to do is I want to choose a well-chosen element of big H to put in here. Because this is true for any element of big H.
How about the identity?
All right, let's try the identity. Okay, so so I can say that. So how do I want to say this? I can say that. Well, I'll break it down a little bit. So the ID is. Why did it get small? Okay, now it's all screwed up. Here, I think if I do this, it will fill up. It will fill up. Okay. ID. No, it doesn't. Let me do it on this side. Okay. Yeah. Okay.
I
ID
love technology.
is in H. Okay. So and that says since H is a subgroup. Right? All right, so that means that so G times ID is in H. And this is the I can say that it's the definition of this is the definition of what this means. That this, if I take what this means here, is that I take G1 inverse G2 times any element in H, and that gives me H. So I'll just say here, so this is the definition of this. Okay. Right? So I'm done, right? Because if I take the identity, if I take this, that's the idea. So this is the identity property. All right, so the key step here was going from here to here. That's the key step. And that's what you have to understand. Now this is a set identity, so it has to be true for every element in the set. Now, notice that I didn't say that G1 inverse G2 identity equals identity. That's not what it says. What it says is that G1 inverse G2 times an element of big H is another element of big H, which may not be the same element.
Right.
All right, so that's very important to remember. When you're equating sets, you're just saying all the elements over here are elements over here. That doesn't mean the result of the individual computation here is going to be the
Which we
same as the
saw
individual
in the-
computation there.
We
So
saw
that's,
that in her example.
so, and you'll see that in other parts also.
So I may be wrong on this, but for some reason, the chapter with the switchboard comes to mind when I look at that. With the inverse and the other one.
Well, let's see, the switch yard you mean. Well,
Because you had the rotations and you had the inverses and.
you do. I don't see an obvious connection now. There's kind of a roundabout connection.
You mean with the permutations?
Yeah,
'Cause
yeah.
that was-
Right.
That was,
That's, yeah.
Yeah, there's some kind of relation, but I can't really put my finger on it.
Well, because I'm just remembering when we did like the R inverse, T, R to the -2, and yeah, that just reminded me of that.
Yeah, well, you've got elements and inverses, and you're playing around with them, but I can't. I mean, well, keep that in mind. Maybe you'll see more connection.
Okay.
There's nothing I can't say anything right now, but all right. So let me just. So that's the second condition. Third condition was here. Here it says that this condition 4, is actually a weaker condition than condition 1. But the reason why it's there is that if you can show one coset is contained in another, then in fact the cosets are equal. You can't. In fact, you can think of this also in linear algebra. If you have two subspaces, and one subspace is contained in the other, and they have the same dimension, they're the same subspace. You can't have two subspaces of dimension 2, one is contained in the other, and it's not the whole thing. They have to be the same thing. So this thing means contained means equality. And this one says that you can flip to the other side also. And you can kind of think of this because you know when you take inverses, you reverse the order. So that's kind of related to this. All right. So I think after we finish this, we can probably spend some time proving this. All right. So we're going to use these facts to show that cosets form a partition. So we're going to use this. Now, some of these you can kind of see why. This basically says that if G1 and G2 are in the same coset, they create the same coset, and one can't be inside the other. So it's basically a whole separate thing that hangs together, and you can't. And every element in the group will be in at least one coset, because I can take that group element and multiply by my subset. So we're going to take these properties and use that to show that the cosets form a partition. So you saw the example of that with modular arithmetic numbers. We saw that also with the triangle, and that's true in general. So that's kind of the idea. That's your raisin bread. All right, so here it says, now let's consider the question of how many cosets there are for a particular subgroup within a given group. So first we define some convenient notation, the index. The index of a subgroup in a bigger group is the number of left cosets. So for instance, let me ask you this. When we took the triangle and took the rotations, what was the index?
It was 3, wasn't
Well, that was 3 was the size of the group. See, 3 was the size of the subgroup.
2.
There were 2 cosets. Okay. And also for Z3, there were 3 cosets. 0, 1, and 2. There were 3 cosets. So the index is just the number of cosets. And then, all right, so here's this example. Let's look at this example. Suppose you have C3, here's my H, and we saw that for H there were 2 cosets, and then there was this other group where you just had a single flip. And you know a flip is its own inverse, so that creates a group. In this case, there were 3 cosets. So you can kind of see the smaller the subgroup, the more cosets there are. Which makes sense because you're dividing the big group up into cosets, and if you take your loaf of bread and slice it into smaller slices, you get more slices. So, all right. So let me ask you this question: Suppose you've got raisin bread, and you've got 120 raisins, and each slice has 6 raisins in it. Then how many slices? 20 slices. Okay. So if you translate that into this language, your subgroup is the number of raisins in each slice. That's the size of your subgroup. The number of slices is the index. So the total number of raisins was the raisins in each slice times the number of slices. And if you translate that into group language, what you're saying is that the size of the entire group, I don't know if it has it here. All right, so it's in the next section. So let me go to the next section. Here it is, yes. The raisins in the loaf is raisins in each slice times the number of slices. Now we're going to translate that into abstract algebra. Raisins in each slice is the size of the subgroup. Then the number of slices is what we just call the index, or the number of cosets. So that's true in general. It's true for raisin bread, it's true for groups. And that's what it says here. So it says, let G be a finite group, let H be a subgroup of G, then the order of this absolute value means order, means number of elements, right? When you have the absolute value for a set, that's always the number of elements. It says the number of elements in the group divided by the number of elements in the subgroup is equal to the number of cosets. So that's just like the raisin bread, but switching things around. It's taking the raisins in the loaf divided by the raisins in each slice, and that gives you the number of slices. Now you can say big deal, but it is a big deal. It's a very big deal, because subgroups are very mysterious things. And if I have a group, how do you know how big the subgroups are? I mean, maybe I have a group of size 20, maybe there's a subgroup of size 7, or subgroup of size 9. How do you know? And this tells you that there's not. If I tell you I have a group of size 20, right away I can tell you there's no subgroup of size 9. Why not?
They are the same.
Well, 9 is not a multiple of 20, that's true. But I mean, what it's saying is that if you've got a subgroup, you can slice the group up into it.
It has to be even.
It has to go in evenly. The size of the subgroup has to go in evenly into the size of the group. So if it doesn't go in evenly, you know right away that it's not a subgroup. And I mean, that's an incredible thing, that you can know right away without knowing anything about the Cayley table, without knowing anything at all about the group, just whatever kind of group, abelian, non-abelian, whatever, really nasty group. So you can have a group that's huge, enormous, and you can say, all right, that the size of this group is not even, so I know there's no subgroup of size 2. And there's no subgroup of size any multiple of 2, right? So you can amaze your friends.
Can't wait.
All right, so
Amaze my students.
yes, okay. All right, now we put that together with what we talked about, cyclic groups. Every element of a group has an order. Every element of a group generates a subgroup. Right? I've seen several examples of this. With S3, you've got one rotation. It generates all the rotations, and it has order 3. So any element of finite group. Any element of a finite group generates a finite subgroup. So what we just found tells me something about the order of elements in a group. I can't have a group of order 20 and have an element that has order 8. I can't. Because if the element had order 8, that would be a subgroup of order 8. I can't have a subgroup of order 8 because 8 doesn't divide 20. Now, this is relating that fact to number theory, that we've talked about the additive group Zn, and we've also talked about the multiplicative group Un. So the multiplicative group n is the numbers less than n that are relatively prime to n. So in fact, that was on the infamous midterm. So you know all about that.
So can we go back to the 1435?
Sure. The remark here? All right, so what does yours say?
When's the exercise?
Exercise.
It's a little bit up.
This one here?
1433.
This one here? Okay. Suppose G is a finite group with element G of order 5 and an element H of order 7.
So the only way that that can work is if it's 35, because that's the least common multiple of them.
Well, but you need to be careful. Could it be bigger than 35?
Well, yes, but the minimum has to be 35 because that's the least common multiple
Yeah.
of it.
Well, the better way to say it is, well, yeah, you can say that. You can say, I mean, you can say.
Well, that's the
you're-
explanation for part
Yes,
B.
yes, that's right.
But then how would you show the subgroups?
Well, what does it mean that there's an element of order 5? What does that mean?
Well, there's...
G has 5 elements.
And this is a little g, not big G. All right, so let's see. Let's copy it here. Oh, here. Okay. I hope.
What happened?
No, it's because I didn't go down first. And now I can do it. Okay, there we go. Well, these are really copying big. Let's zoom out. Okay. I don't think I can probably move this back here. All right. So that's my question. My question is, what does it mean that? Well, you can't even see it. It's over on the side. So, G. So the order of G is 5. So what does that imply?
Well, Chrissy said 5 elements.
What has 5 elements?
G.
Little g.
Little g is an element. Now, those absolute values mean several things. Now let's go back to the cyclic group section.
Maybe like little g, big G.
The little g is not a set.
No,
No, I
little
was
G
saying
is an element.
an element. So the absolute value on an element does not mean the number of elements in that element, which is 1. It means
Okay.
something else. So let's go back
Could
to
it
the chapter.
mean, like
Let's go
it's
back
the
to the
number of
chapter.
times that it can be ordered.
Well, let's go back to the chapter.
Yes.
This
I
is
know.
this is the part about
It's been a
cyclic
while since
cyclic
we've
groups.
talked
Yes.
about
Okay.
that.
Yeah. That's right. Okay. All right. So here, let's see. Now, do you remember these angle bracket things here? You take an element
Yes.
and you multiply it by itself, multiply by itself again, and then you also do the same. We did this in elliptic cryptography too. We multiplied elements by itself many times. So you have these angle brackets. Now this is not the straight brackets, but the straight brackets are related to that. Let me find it. All right, so here, here it says here is that this, if I take a and a squared and a cubed and a fourth and so on, it's going to give me a subgroup. It's going to create some subgroup. Okay. All right, now here we go. Here we say the order of an element is the smallest positive integer such that a to the n is the identity. So for instance, let's ask this. Suppose I take a triangle and I rotate 120 degrees. Equilateral triangle, rotate 120 degrees. What's the order of that rotation? There's 3, because you can do it 3 times and come back to it. And you know if you've got a pentagon, then you take whatever that angle is. It's 72, I think, right? 72. So if you do 72 degrees, then what's the order of that rotation? Or let's use square. Okay, square is 90 degrees, right?
4.
What's the order is 4, because 1, 2, 3, 4, and back. Okay. So I took that one group element, which is the 90-degree rotation, and I generated all the rotations, and the number of rotations in that subgroup is 4, because I created them one by one, first by rotating 90, then 180, then 270, created them one by one. So the number of elements in that subgroup is called the order. So what it's saying here in this problem
No, you have,
I went too far, right?
yeah, it's 433.
All right, well, I'll just go to the next one here. Well, here, I'll go here. All right, so what does this mean? This means that the subgroup that's created by this is G squared, G cubed. How far do I go?
5.
Okay. So what is G to the 5th?
The identity.
G to the 5th is identity. Okay. All right, so that means this is a subgroup.
And then you do the same thing with 7.
Yes, so I can copy this and replace my G with H. And then this becomes H squared, H cubed, H to the 4th, H to the 5th,
H to the 6th.
H to the 6th, and then the identity. Okay. All right, so, oops, okay. All right, so now what did we just learn about Lagrange's theorem? Lagrange's theorem says that the order of a subgroup must divide the order of the group. Okay. So here we have 2 subgroups. So the key is that the order of G doesn't mean that G has 5 elements. It means that G generates a group of 5 elements. And the order of H is 7 means that H generates a subgroup of 5 elements.
7.
7 elements, yes, okay. 7, 5, same thing. It's all less than 10.
The scale of
Yes.
infinity.
Right. So all right. So that means that. So this implies. Now remember that this means the number of elements in the set.
Right.
So is divisible by
35.
5 and 7. Right?
Yes.
And
Therefore, it must be divisible.
so it must be divisible by the GCD.
And we can't use that proposition that we had proven earlier, because those are elements. No,
One,
I'm
those don't
talking
say
about
any-
like the 1 through 5.
Those don't say
Okay.
anything about order though.
Not right. Well, what you needed to do. Well, Lagrange's theorem follows from that 1 through 5.
Okay.
The key fact that you're using is the Lagrange's theorem. But this doesn't tell you anything about how G creates a subgroup. The key fact is that each element has its associated subgroup.
Okay.
That's the key thing that you take from the previous chapter. All right, so you okay?
Yeah.
All right, so that's Lagrange's theorem. And all right, so what I was saying here is that I think we showed that the when you take the multiplicative group UN, the number of elements in that group is the number of elements, number of integers less than n that are relatively prime to n. I believe that we showed that.
Can you say that one more time? I'm
So
sorry.
all right, so let's take an example. Suppose I take u of 9.
Mhm.
So let's look at u of 9. What are the elements in u of 9? 0 is not there. 1 is there. 1 is always there. What else is there?
2,
2. What else?
4,
4,
5,
5,
7,
7,
8.
8. Oh, now, how did you choose those?
They're relatively.
Those are the numbers that are relatively prime to n. Those are numbers less than 9, relatively prime to 9, right? So I should say positive numbers. All right, now I can just replace the 9 with an n. Right? That's true for any n. Of course, I can't say 2 is there, so I'll just say 1 dot dot dot. So positive numbers less than n, relatively prime to n. Now there's a function called the Euler Fee Function. And that's defined as the number of natural numbers which is positive integers less than n relatively prime to n. So phi of n is defined to be this number. And so it's created by this guy Euler, who's from Houston.
Are you sure?
Yeah.
Like, seriously?
Yes.
He's from Houston?
Yeah, he's from Houston. Haven't
He's
you?
an Euler.
Yeah, the Houston Oilers. Haven't you heard?
No. Okay.
Right, well. So, and you can actually prove some things about phi.
Where have we used
So the
that
greatest
before?
mathematical improvements for during the oil boom.
Mhm.
Yes.
I'm sure.
All right, so then this is just applying that stuff. Now, for instance, if you look at this, all right, so what do we have here? What does this say? The order of the group, like if I take 23, right? The order of U23 is this number, whatever it is. The order of U23 is this number.
Which would be 1. No, there's a lot of numbers.
No, there's a lot of
Yeah,
numbers here.
I
There's a
was
lot.
thinking of-
In fact, it's 22, right? Because
Yes,
23 is prime.
Yes, that's
Okay.
right.
So all right, so let's take these. There's 22 numbers in P of 23. Now, if I take any element in U of 23, the order of that element must divide 22.
Okay.
That's what we were saying. If I take an element,
Mhm.
and so what does the order mean? The order means I take that element, then it's squared, then it's cubed, and so on.
Mhm.
We take a squared, a cubed, so blah, 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 blah. Now, the order that's generated has to be divide 22. So suppose I take, well, all right, so let's write this. Let's suppose, so let's do an example. Let's take U of 23. U of 23. So the size of this, as I said, is 22. 'Cause it has, so I'll just write that just to be careful. 1, 2, 3, dot, 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 up to 22. And that has 22 elements in it. Okay. So let A be in U of 23. Okay. That means that you get some, if I get this A squared, A cubed, dot, 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 is a subgroup. of U23. Okay. So that means the order of this the order of this must divide 22. Let me write here, I don't know what this last power is. I'll write it x. All right. So what does this tell me about x?
It has to be smaller than, less
Smaller
or
than
equal
22,
to
yes.
22.
Yeah, it has to be less than or equal to 22. Anything else? Well, how many elements in here? How many different elements in here?
22.
X.
Well, yeah, you don't know it's 22, you only know it divides 22. There are x elements. So in fact, this is equal to x. Okay. Now we know, now in this case, you know what a to the x is. What is a to the x must be equal to? What's the last element in this sequence?
22.
No, a to the x. No.
1.
Yes, a to the x is 1. Because that's when it starts to cycle. The last one is when it starts to cycle. Okay. So that means that x divides 22. Oops. X divides 22. And a to the x, I shouldn't say equal 1, I should say congruent to 1. So let me just write this way, because and a to the x is congruent to 1, and that's mod 23. Okay. Right. So what does that tell me about a to the 22?
That's also equal.
Okay, very good. Why?
Because mod 22, or mod 23, the remainder is 1.
I wonder if I do that. All right, there, I got it. Okay. Okay. A22. Well, I can write this.
Because there's 22 elements, and the last element is 22.
All right, but that's, well, you don't know the last element is 22. And there's not 22 elements. There's only x elements here in this one. There's 22 elements in the whole group, but this doesn't give me the whole group. It only gives me part of the group. But how can I get a to the 22 from a to the x? What's the relation between a to the 22 and a to the x? Using the fact that x divides 22.
A to the 22.
Can I express this in terms of x somehow?
Can we say 23 minus x?
No. Yes, I want to use this. I want to use this here to re-express. I want to re-express this in terms of x. Or in terms of a to the x.
A to the power of some number times x would equal this a to the power of 22.
Okay. So you're saying that, yes, 22 equals, all right, good, let's do it that way. So that means that, let's put that here. So I can write 22, since x divides 22, I can write 22 equal kx, where k is an integer.
That's for equation.
Okay. All right. So a to the 22, so then I can just say a to the 22 equals a to the kx.
Oh, okay, yes.
All right. So that's something I can do. Now, what can I do with this?
Well,
Use your exponent rules.
well, 22 equals kx.
A to the x is 1.
The a to the x is 1.
And 1 to the power of anything would still be 1.
Yes.
plus 23.
Yes.
Why?
So say it again.
A to the x in parentheses to the power of k.
All right, there's your exponent rules. Coming back to font sheet.
And we've already said that a to the x is congruent to 1 mod 23.
Yes. Okay, so I'm going to say equal because we're operating in the group. Okay. Well, or we can, maybe we can do it that way. I'll say is congruent to 1. We'll just say that mod 23. So this is equal to 1 to the k, mod 23. And that's equal to 1. So what did we show? Here we took any, let me emphasize, any element of this. I didn't say which one it was, I just said any old element, whichever one I want. Then this is always true, no matter what A is. And then that means, and I just rewrote that, and said that the number of elements must divide 22, and that's by Lagrange's theorem. Okay. So that means x divides 22, and we also have a to the x is equal to 1. That came from up here. And then we concluded that no matter what a is, a to the 22 is congruent to 1 mod 23. Now that was obvious, right? But that's what you have. So the conclusion is that a to the 20. The conclusion is that I'll underline in boldface is that a to the 22 is congruent to 1 mod 23 for any a in 23.
So what can we say in general then?
Well, all right. So what did we do here? So let's generalize this argument. Let's take this and we'll generalize it.
Or I.
All right. So let A be any element of U of n. Right. So this is a subgroup of U of n. So this must divide. What must it divide?
N minus 1?
No, not n minus 1. What's the size of U of n?
Oh, n.
No, it's not n either. It's this thing.
Oh, yes. Okay. I'm sorry.
Okay.
With relatively
Yes.
prime, not
Yes.
all the integers,
Yes.
just the relatively prime. Okay.
So I'll just say, okay. Okay. All right. Let me just tell Jordan I'm in class right now.
Or is it fee?
Yes. Okay. All right. So this is. Let me just say phi of n. Actually, I can do this. Right. So this is from Lagrange's theorem. So that means x divides, no, it's not 22 anymore, it's this phi of n. And a, instead of this x, well, a to the x, okay, and this is mod n. Okay. So here I have a phi of n. I can just do this, I think. That still holds. And then this means here, instead of the 22, I put the phi of n. It didn't like it. Can I move it up? It won't let me move it up. So I'll do it this way.
Probably because of fee.
I guess the phi is fixed. Or I can do this, I can do it this way. I can just do it this way. Is it going to work? Let me try it. Yeah, it works. Okay. Okay. So this is still true. This is still true, and this is still true, and this is still true mod n. So my result was that this can go into 1 mod n for any a.
Okay.
And that's number theory. Number theory really is a lot like magic. These things just happen. But when you come right down to it, it's counting. Things had to divide things, and that's how it worked out. So then this is just working out some consequences. And did we get to 14.4 or just, I think we started 14.4, right? What was the...
14.46 is the last one.
Okay, all right, so let's look at the first couple here. All right, now, so far we've been talking about any old subgroup. And I can say also that we've been talking about cosets. There are two kinds of cosets. There are left cosets and there are right cosets. You can multiply the element on the left, like this one, or you can multiply the element on the right, like this one. And there's no guarantee that those cosets are the same. There's a special kind of subgroup called a normal subgroup that says that all left cosets are right cosets and vice versa. And this kind of subgroup is very important and has some special properties, and we'll get into that. It turns out that I'll say it, but it may not completely sink in, but it turns out that if you have a group and a normal subgroup, then the cosets of the normal subgroup form a group in its own right. So let me say it again. If I got a big group and I have a normal subgroup, then the cosets of the normal subgroup form another group. So from one group I created two. I have the subgroup and then I have the cosets of the subgroup. And in the way this is called factoring the group. You're factoring the group into cosets and the subgroup. So we don't get into that this week. We just get into the definition of normal subgroup. So maybe I should stop there. And I think I'll stop recording.